Hey guys, this video is going to be about different types of solids. So let's get started. Alright, so first we're going to talk about the different phases of matter, and I know that you all know all this, but just to make sure, there's solids, liquids, and gases. We're not going to talk about plasma. Solids, they have very little energy in the atoms or the molecules, and they make up their own shape. So if you put it in a container, it doesn't take the shape of the container. It doesn't fill up the container unless you put enough in there to fill it up. And there are two different types that we're going to talk about. There's crystalline. It's the most common type that we look at, and it usually forms a crystal lattice structure and is uniform and repeating. And amorphous solids they form irregular patterns in the atomic structure or the molecular structure. Liquids are particles that are still very close together. They're much closer than the way they show them to you in grade school. They're actually almost as close together as solids, but unlike solids, they have more energy. And so they're constantly colliding with one another and rolling over each other and stuff like that. So they're in a lot more motion, and they take the shape of the container, but it doesn't fill it. So the molecules or the particles won't expand to the shape of the container. They just take the shape of the container, like the bottom shape. So the second picture here is a liquid. And then gases possess enough energy to overcome all of the intermolecular forces. So there's no forces of attraction or repulsion between them anymore, but they just expand to whatever container that they're in. That's why in your bedroom, there isn't more oxygen or air, for that matter, at one side of your room than on the other side of your room, or it fills up the entire room. Gases will always expand to the size of the container that they're in, and they move completely freely with lots of space between them. And so they have high energy. So just to remind everybody, when it goes from a solid to a liquid, it is melting. And we use the delta H of fusion for that to show how the energy is transferred. From liquid to gas is vaporization. And so you'll see delta H of vaporization. The opposite of vaporization is condensation. And then the opposite of melting is freezing. And then the big arrow from solid to gas is sublimation, and from gas to solid is deposition, to deposit something. All right, so two different types of solids that we mentioned were crystalline solids and amorphous solids. And so I'm going to talk about amorphous solids first because we're not going to mention them again after this. And so amorphous solids are things like rubber, and the atoms aren't arranged in any particular order. They're just really close together and they don't move much. They just kind of vibrate in place, but there's no order to how they're arranged. With crystalline solids, on the other hand, and everybody should recognize this from on my desk as sodium chloride. Okay, so the purple balls are the sodium ions, because remember, positive ions get really small and shrink because they lost electrons. And then the green ones are chloride ions, and they get bigger because they've gained electrons. And so it has more electrons than protons, doesn't pull it in as much, so it's going to get much bigger. And it's not just one sodium and one chloride. It's one sodium to every chloride. So every sodium here has 6 chlorides attached to it unless it's on the face. And every chloride has 6 sodiums unless it's on the face. So it is 1-to-1, but it forms these crystalline lattice structures, these huge crystalline structures. And that's why little pieces of salt look like little crystals. So it's uniform in composition, it's repeating patterns, and there are several different types of crystalline solids that we're going to look at. All right, so the 4 different types is, the first one is ionic. And ionic is an electrostatic attraction of 2 oppositely charged ions. Usually it's a positive metal ion and a negative nonmetal. So for magnesium bromide, it would be magnesium bromide, MgBr2, sodium chloride, NaCl. So those are ionics. Metallic is delocalized sea of electrons shared by many positively charged metallic ions. So something like iron or copper would be a metallic solid. A covalent network is a massive network of covalently bonded atoms. So diamond is an example of that. And we'll take a look at all these in closer detail in just a minute. And then molecular is molecules in the solid form attracted to one another by intermolecular forces. Now, these are really the ones that usually do not exist as a solid at room temperature. They're usually liquids or gases, but we still have to look at how they behave as a solid. And so we just have to get them below their melting point to be able to see that. All right, so this is water, carbon dioxide, things like that, sugar. So let's see, glucose. Those are molecular solids if they're in the solid form. All right, so looking closer at ionic compounds, I said before they're electrostatic attraction. Electrostatic just means we're looking at charged things that are attracted to each other because they're opposite in charge. And it forms a 3D crystal lattice structure. And this structure causes these solids to be brittle, conduct electricity in liquid form and aqueous form, non-conductive in solid form, have extremely high melting points. So we're just going to use this big sodium chloride thing, and I'm going to draw a mallet up here. Okay, so this is my hammer. And if I was to hit right here on this, it would push this sodium down one, and then everything else would be pushed down one. So then we would have this purple sodium ion here, right next to this one. And so you would have a sodium next to a sodium, and those things are going to repel each other, and so that whole piece is just going to fall off. And that's why if you hit a rock of table salt or Epsom salt or whatever with a hammer, it turns into dust because it's brittle and it just falls apart, because then you have positively charged ions next to positively charged ions, negatively charged ions next to negatively charged ions, and they just repel each other and it just turns into dust. When we melt it, so if you have table salt and you get it to a high enough temperature, it's extremely high, and you melt it, it actually turns into liquid ions. And so now you have something that's going to conduct electricity because it's an electrolyte form, because it has these ions. And remember, electricity is just electrons, and so it's going to be able to flow through those ions better. And the same thing happens if we put it in water. It dissociates into ions. But in the solid form, if we were to put a conductivity meter into a solid sample of sodium chloride, it would not conduct electricity at all. And they have extremely high melting points because in order to overcome this, you've got to heat it up pretty good. And if we were to compare something like this is the crystal lattice structure for calcium chloride, and it looks a little bit different because chloride has 2, calcium has 1, and we're not going to go over how you would figure that out from what this is called a unit cell. It's just 1 unit. But there is a way, and if you go further into chemistry, you learn all that. But for calcium chloride, since there are 2 chlorides here, that means that calcium has a +2 charge. And so there would actually be a higher attraction between those two because of the charge. So that's Coulomb's law. And remember, Coulomb's law looks something like that. And so if one of those charges is a 2 instead of a 1, it's going to have a higher attraction. And so that's what would happen with that. So this would have a higher melting point than sodium chloride would because it has a 2+ charge. If you were looking at something like lithium chloride versus sodium chloride, then you would say, well, they're both chlorides and they're both +1, -1, but lithium is smaller. And so since lithium is even smaller than sodium, that means that their nuclei can get even closer, and so the R would go down. And so that's when you're looking at the size of the ion. So if the ionic compound has smaller ions, they're closer and stronger bond, which means a higher melting point. If it has a bigger charge than Coulomb's law, and this is all because of Coulomb's law, anytime you're looking at electrostatic attractions, you're looking at Coulomb's law. If it has a higher charge, like the calcium has a higher charge, then it would also cause a higher force of attraction and cause a higher melting point. All right, so crystalline solids, metallics. So metallics can be described as a sea of delocalized electrons shared by many positively charged metallic cations. All right, so delocalized. Let's take that word apart and see what it means. It means not local. So they're not forced to be in a particular bond in a particular way. So basically, we can say that this is going to be copper. All right, so this would be a sample of copper, and it does form a 3D crystal lattice like in here. And the structure and bonding causes these solids to be malleable and ductile, have relatively high melting points, and conductive in the solid in all directions. So basically what happens is this copper releases an electron. So each copper atom releases an electron to its environment, and it's shared by the entire environment. So they're the socialists of the group. You have all of these copper pluses, and these electrons are free to move about. Remember, they're delocalized, and so they move all over this piece of metal. They probably stay somewhat close to their original atom, but they still have the freedom to move wherever they want. And the electrons, then, if we were to apply electricity to this piece of metal, the electrons that are in the electricity can just move with them. And so then all of these electrons start moving in the same direction, and we can conduct electricity. Not only that, but if I was to take my hammer here, because those electrons aren't given to another ion, if I hit this with the hammer, then these can just move closer together. It also makes it malleable. They can get closer together. We can pull them into wires, all sorts of stuff. So now I realize that there's a positive ion next to a positive ion, but there's no negative ions where these electrons are being held. So this can just move down and get closer, and they're all still sharing the electrons. So it's completely different than in an ionic compound. All right, so crystalline solids, covalent networks. Okay, so covalent networks are the weird ones out of the group. They're massively networked of covalently bonded atoms, and they form a 3D lattice structure, and these structures and bonding leads to extremely high melting points, very stable bonds. The conductivity varies from structure to structure, but most are conductive, or most are non-conductive in solid form, and they don't dissolve in water. So you add it to water and it just kind of sinks to the bottom. All right, so the first one that I'm going to look at here is diamond. And if you remember the things that are hanging in my classroom to your right next to my computer, I had a big model of diamond there and a big model of graphite. So each one of these atoms is a carbon atom. And carbon really, really likes the sp3 hybridization. And each carbon is sp3 hybridized to another carbon that's sp3 hybridized. So each carbon is tetrahedral to each carbon. And so it's in its most perfect bonding pattern with another carbon. And it makes it incredibly strong. And so this thing just continuously grows bigger and bigger and bigger. Things like diamond, silicon, some forms of glass can be covalent networks. Other forms are actually amorphous, but this is actually a covalent network, silicon dioxide. But you have silicone to each oxygen, and then this goes to another oxygen that's to another silicon. And so it just keeps going on and on and on like that in these big crystalline structures. And it forms these massive covalent networks. And that's why they call them a network. Just like a social network, you have friends of friends of friends of friends, and it just keeps going on and on and on. A covalent network is a bunch of covalent bonds, but it doesn't ever stop. Like with sucrose and water and even biomolecules, there's an end to that molecule. Covalent networks, it doesn't have to stop. It just keeps going. So graphite is the weird one in the group. That's what your pencil lead is made out of now. But each one of these is a carbon atom, and they form these 6-sided hexagon shapes. And so each carbon then is also, so there would be another one here, and then another one here. And so each carbon is bonded to 3 other carbons in a flat 2-dimensional plane. And so there is actually another electron underneath all of these that's kind of free to move about. And that's why graphite actually conducts electricity in one plane only. So each carbon is bonded to other carbon atoms. And so it has an extra electron free to move about in one plane. And that's why graphite can conduct electricity. It's also why you can write with it. It kind of shaves it off. And so even though it has a high melting point, it's not nearly as hard as diamond is to break. Obviously, you can break pencil lead very easily. So some of these properties are going to change from compound to compound. You should be able to determine, if it was a multiple choice type question, whether your substance was a covalent network or an ionic compound. All right, and then the last one are molecular solids. And this is where students, I think, make their biggest mistakes, because we're talking about, in metallic solids, we're talking about how it's bonded together. And in ionics, we're talking about how they're kind of bonded together. But in molecular solids, it's not how they're bonded together. Because if we look at water, right, water has covalent bonds. The bond between, but that's not what making it a solid. What makes it a solid is how close together those water molecules are. So I put here a sucrose molecule. So sucrose is much bigger than glucose. It's almost twice as big. It actually has a glucose in it and a fructose in it. So that's a big, huge sugar molecule. You don't have to know what that looks like. But this would be a three-dimensional structure of it, the way it's all bonded together. So it kind of looks a little twisted up somewhat. Okay, so these big, huge things are sugar molecules. And this was really the only thing I could find that showed it how it would be a solid. So because all of these are OHs, just like in water, this thing can hydrogen bond with itself. That would be its intermolecular force that would be holding them together. And so you can see here how they would be attracted to each other from one OH to another OH. And so there would be attraction between, like, this oxygen here, and that hydrogen there. And so it would happen all over the place, where an oxygen was attracted to a hydrogen on the neighboring thing, and they would just stack on top of each other and form these crystalline structures. And that's what it's made from. Okay, now, and that's another reason why we can dissolve it in water, and it will actually dissolve, is because the water also can hydrogen bond, and so the sucrose can hydrogen bond with the water molecules, and it will dissolve in the water. Now, not all molecular solids can do that, because not all of them are going to be polar. But I wanted to show you a picture of one that was, so that you could see what's actually happening. So when sugar dissolves in water, it's because there's a bigger and better attraction between the water molecules and the sugar molecules than the water molecules have to each other, and then the sugar molecules have to each other. And then that's why it happens. The big point here is that when sugar is in the form of a solid, it's because the different sugar molecules are attracted to one another. It's not just one sugar molecule that you're holding when you're holding a grain of sugar. There's billions of them in there. These things are not conductive by themselves. They don't have any free electrons to move around. And they have relatively low melting points. We can melt sugar in our kitchen on our stove. So only the intermolecular forces have to be overcome. We're not actually breaking bonds when we melt something. We're only breaking the intermolecular forces, and so we're only overcoming those forces between them. And so in this picture, this is a picture of water in ice form, so water in solid form, and it forms, you can see the crystalline structure there. So every single one of these is a water molecule. There's a water molecule, and there's a water molecule, and there's one back there, and here, and one in the back. And so each one of those is hydrogen bonded to another one. And they form this pattern, this repeating pattern in ice. And so, but that's only when it's in ice. When we melt it, they're still going to be hydrogen bonded together. And the coolest thing about water is that when we melt it, the hydrogen bonds are actually, the molecules get closer together, but they just move around more. It's more dense than in the solid form, which is unusual. And then we have carbon dioxide here, so CO2. And I put this one on here because it doesn't have hydrogen bonding, because it's nonpolar, and so all these are held together by London dispersion forces. That's the only thing it has. It's not polar. It doesn't have hydrogen bonding. The only intermolecular force that it has going for it is London dispersion forces. And they just get really, really close together because of those unequal distribution of electrons that just happens to pop up and then forces the next molecule to have them as well. And then this would be iodine, I2. So you have each iodine molecule. There's 2 I's there. And they're also attracted by London dispersion forces, and they form a solid. Iodine is one of the only halogens that's in the solid form, other than acetine, which doesn't last but for a few minutes or seconds or whatever. So it doesn't really count. So its attraction between the molecules is just going to be London dispersion force. All right, and then the last 2 things that I want to talk about are the 2 different types of alloys. There's interstitial alloys, and then there's substitutional alloys. And interstitial alloys is when much smaller atoms are added between metallic atoms. And so it changes the property of the original metal. And it's usually done to prevent corrosion, oxidation, and to strengthen it. So here, down here on the bottom, or on the bottom left, we have your pure metal. So whether that's iron or whatever, that's the pure metal. And then we've added these little bitty atoms, and they're usually nonmetals, because nonmetals are generally pretty small. And so with steel, what we've actually added is carbon atoms. So if you look over here on the right, there's 2 different types of steel here. There's a lot more than this, but these were the best pictures I could find. And so you have all these iron atoms, and we insert these carbon atoms in the middle. And what that does, if I try to hit this with my mallet, these can't get much closer together. So we can create these huge sky rises, and it can hold all these weights, and the iron won't crumble under the forces that are being applied to it with all the weight of everything else that's sitting on top of it. And so that's why we make those. The other type of alloy is a substitutional alloy. In a substitutional alloy, metallic atoms are substituted for other atoms of similar size. And so that changes the properties of the original metal. And it can be done to change the color, malleability, some of the same reasons as the one above. But one thing that I know that I have seen is pink gold. And pink gold, a little bit of copper is added to it, and that makes it pink. So one that you probably are more familiar with is brass. So brass is a substitutional alloy where they take zinc and copper and they kind of mix it together, and it looks like this. So what would have been all copper atoms now has a bunch of zinc thrown in, and it's just to change the malleability of that metal, and so it can be manipulated in a different way. And then you can also mix those 2 together to make it even stronger. And so that's basically it for this, guys. Let me know if you have any questions.